Hey everyone. In the previous video I talked about an interaction between a continuous variable and a dichotomous independent variable, right? And we talked a bunch about how to interpret these interaction terms. In this case, we want to kind of dive more into different types of interactions because the interactions that we're modeling are don't necessarily involve one dichotomous indicator and one continuous indicator. And if that's the case, the interpretation slightly changes, okay? So now in this case, we're still looking at interactions. So we have two independent variables, x1 and x2, and the interaction, which is the interaction coefficient, which is the coefficient associated with the product between x1 and x2. But now we're looking at two additional kind of sub-cases. One is where x1 and x2 are continuous, so both are continuous independent variables, right? If that is the case, of course, we can't really make this interpretation that we did in the previous video where we said the slope changes from group 1 to group 2, or say how this kind of shift between group 1 and group 2 changes across ranges of x1, because we don't have two separate groups according to the second variable x2, right? So as soon as that's the case, as soon as we have two independent variables that are continuous and we have the interaction between the two, we kind of have to change the interpretation a little bit. When it comes to the main, what is often called the main effect, so kind of the beta 1 parameter in this case, so the effect of one of the continuous independent variables. This could also, the same of course applies for beta 2 x2. The key is that this is the coefficient for not the interaction term, but for the one of the independent variables that is part of the interaction by itself, right? So how to interpret that specific coefficient? The key here is that, again, holding everything else constant and x2 equal to 0. So the other variable that is included in the interaction is held equal to 0. A 1 unit increase in x1 is associated with a beta 1 increase or decrease in the expected value of y. So not so much has changed except for the fact that this x2 that is now held as equal to 0 when we interpret beta 1, this x2 doesn't take two different values, 0 or 1, but it can take a whole range of values, right? And now things can get a little bit more complicated. For example, I mentioned in the previous video that we had cases when it comes to interpreting the intercept. For example, if you have an independent variable like GDP per capita, if you're looking at, comparing different countries in your data set, the interpretation of this beta 1 coefficient now depends on x2 being equal to 0. So if your x2 is something like GDP per capita, which in your actual sample is actually never equal to 0 unless you mean center it, for example, then this beta 1 parameter doesn't really have a sensible substantive interpretation because it's basically an extrapolation of the effect beyond kind of the range of data or values for x2 that you actually observe, okay? So in order to avoid this, what is done oftentimes with interactions with continuous variables is to mean center them. So to subtract the average value of x2 of all observations of all values of x2, so that the average is 0. So that means, of course, that then this beta 1 the interpretation of beta 1, the coefficient for x1, is then the effect of a 1 unit increase in x1, or on an increase or decrease in y when x2 is equal to 0, which now means x2 is equal to its average, okay, which of course is not an extrapolation beyond kind of the range of reasonable sensible values that you usually see, right? So that's why mean centering is so important when you have interactions with continuous independent variables, okay, to make these main, so to speak, main effects kind of interpretable. And then next, when it comes to the interaction term, again, it becomes a little bit more complicated because we don't have these nice two groups that we can compare, and we can say, okay, the slope is different between group 1 or group 2. It becomes more complicated in the sense that now we have a continuously changing slope, not between x1 equals 0 and x2 equals 0 and x2 equal 1 with two different slopes, but rather x2 ranges across, since it's continuous, it ranges across a large number of values, and the slope of x1 kind of changes accordingly. Okay, so the interaction term between two continuous independent variables can then be interpreted as holding everything else constant. A 1 unit increase in x2 increases or decreases the average change in y associated with a 1 unit increase in x1 by beta 3. Okay, so this sounds a little bit more confusing than in the previous scenario, but kind of if you consider back our previous simple example of an interaction between a dichotomous indicator and a continuous independent variable, you could think of this as one special case where x2 just takes the value of 0 and or 1, where we have the slope changing to beta 1 plus beta 3, right? But now just imagine that there's instead of just being two different slopes and two different groups, imagine that there are just a continuous range of possible values that x2 can take, and so the slope kind of changes not between those two groups, but gradually changes. X2 increases in value, the slope becomes larger and larger and larger, up to where x2 is equal to 1, we're here, but x2 can take even larger values, and then the slope could be even steeper. Okay, so it's kind of just an extension of the same argument that we had before, just now having two continuous variables that are interacted with each other. So we're having a continuously changing slope depending on the level of the second variable when we look at the effect of a 1 unit increase in the first variable. Again, another thing that holds similar to the arguments that I discussed in the previous video, we can interpret these interaction terms kind of in two different ways, right? We can focus on how x2 changes the slope or the expected change in y associated with a 1 unit increase in x1, but we can also flip it around. The interaction term equivalently tells us how the slope of x2 or the effect, the change associated with a 1 unit increase in x2 depends on x1, right? So both are equivalent. We can kind of think of as one changing the slope of x2 or x1 changing the slope of x2 or x2 changing the slope of x1. Both are equivalent, and again, similar to how we talked about here, we could think of this interaction term as telling us how this shift changes or this slope changes. Both are mathematically equivalent. This interaction term also kind of interpreting it as one variable being the moderator and the other one being the effect that is moderated can be flipped around depending on your substantive interpretation depending on your substantive interest. Okay. Lastly, we talked about a case where x1 and x2 are continuous. We talked about a case where x1 is continuous and x2 is dichotomous. Of course, we can also have a scenario where both x1 and x2 are dichotomous, so both are just coded 0 or 1, and we include an interaction between those two. Right? As soon as we have that, the interpretation again changes just slightly. When it comes to the independent variables, so for example the effect for beta 1, but again the same holds for beta 2 x2, we can say that holding everything else constant and x2 equal to 0, so always the opposite variable is equal to 0, that is included in this interaction term, the expected value of y is increased or decreased by beta 1 when x1 is equal to 1 instead of 0. So this is similar to the interpretation of the dichotomous independent variable that we talked about previously, but now again just keeping in mind that x2 is equal to 0. Right? The interaction term beta 3 x1 x2, or the beta 3 as the coefficient, is again can be interpreted similarly, but there's a subtle slight change. Holding everything else constant and x2 equal to 1, the expected value of y is increased or decreased by x1 plus x3 when x1 is equal to 1 instead of 0, right? So now keep in mind that both x1 and x2 are dichotomous, right? So we're not really talking about a slope because none of the independent variables are continuous, right? So all we see for x1 is the effect, the change in y that is associated with changing x1 from 0 to 1, right? Switching from 0 to 1 in x1, right? And so the interaction term then tells us how much this shift from 0 to 1, or how much this effect from x1 going from 0 to 1 changes when x2 is equal to 1 rather than being equal to 0, right? So rather than looking in the reference category where x2 is equal to 0, we're now looking at the alternative group where x2 is equal to 1, and the change in the expected change in y is now not only beta 1, but it's beta 1 plus beta 3, kind of following the same argument here. X2, when we interpret the beta 1 coefficient, x2 is equal to 0, so those drop out. So an increase in x1 leads to a beta 1 increase in y. If x2 is equal to 1, and we look at this as a function of x1 and increase x1 from 0 to 1, we don't only add one beta 1 here, but we also add a beta 3 here. So the combined effect of x1 changing from 0 to 1 is beta 1 plus beta 3, right? And so one thing that is important to note, I'm just mentioning this because we talked about difference in differences before. If you go back to our discussion of the difference in difference estimator and kind of the logic behind the difference in difference estimator, beta 3 is essentially the difference in differences estimator, right? If we have two different, we talked about this wage increase in the minimum wage example where we had two different states. One increased the minimum wage and one didn't, and we had kind of four different measurements, right? One pre law change and one post, or one pre minimum wage increase, one post minimum wage increase in two states. I think it was New Jersey and Pennsylvania, I believe. And so the difference in difference was kind of not only the change from pre minimum wage increase to post minimum wage increase, but it was how that change shifted from one state versus the other state, or one group versus the other group, right? And so if we analyze this in a regression, we could model this kind of difference in difference as an interaction between the state that each of those restaurants were in and whether it is pre minimum wage increase or post minimum wage increase, or whether the minimum wage was increased versus not, right? And so the difference in difference estimator is then shows you kind of how much the unemployment or employment and so on changed in that example in the treatment group versus the control group in the comparison pre and post. Okay, so in that sense, the beta 3, the interaction term, is the difference in difference estimator, or is mathematically equivalent to the difference in difference estimator that we talked about in some of our previous weeks. All right, so that concludes our discussion of interaction terms. In the next case, we're going to talk about quadratic terms.